Hello, in this video I'm going to give a little bit of background to Ludwig Boltzmann, the Austrian physicist who is probably best known, I suppose, for making that link between classical and modern thermodynamics. He brought thermodynamics into a whole new domain, really, by, well, developing statistical mechanics was the main thing. I mean, along with James Clerk Maxwell, he was very much at the forefront of considering substances in terms of these constituent particles, massive numbers of particles. First they were looking at gases, and then Boltzmann moving into liquids and solids off of the back of Maxwell's work. So he was born in Vienna in 1844, and that's where he later studied maths and physics at university. He became professor of mathematics. He got married, he had 4 children, and then he became the head of experimental physics at the University of Graz, which is also in Austria. They probably pronounce it differently to that. And he was the head of experimental physics there for 14 years. And that was where he developed the first version of statistical mechanics, really started laying down the foundations for that whole new way of analysing this particular part of the world. Now, in later life, he had a lot of mental health issues. There's been some speculation from biographers who have been looking at his notes and what people said about him at the time, that today he might have been considered to have bipolar disorder. And he had some serious mental health issues, to the extent that when he was only in his early 60s, he committed suicide by hanging himself. So he had a very tragic end while on a family holiday. He, as I mentioned before, he was very strongly influenced by Maxwell. And Maxwell was the person who was perhaps first really introducing statistics into physics. And this, I suppose it was a contested area, really, because it was before the atomic theory had really been set up. So, you think that atoms and subatomic particles and such like were, well, they hadn't really been detected properly until the late 19th century. So there was a little bit of a conflict going on in the world of physics, of those who were thinking of gases in particular in an atomic way, having these particles flying around, and it was these particles that were creating the pressure inside gases, or whether it was going to be something more to do with energy. Of course, back then a lot of people were still thinking of energy being and heat flowing through a substance, the ether that some people were thinking was permeating the universe. So where was this pressure coming from? Was it coming from a substance? Was it coming from the energy? Was it coming from this atomic theory? And it was Maxwell and then Boltzmann following on from what he had read, because Maxwell was only sort of 10, 15 years older than Boltzmann. And Boltzmann was following along, and he was taking this statistical route of looking at these atoms or particles that were creating the gas pressure. And of course, the two of them, Maxwell and Boltzmann, although they were working independently, they both came up with the Maxwell-Boltzmann distribution, which is what's used when describing ideal gases, for looking at energy distributions and such like of the particles that are in the gases. So that was one major breakthrough that was going on there. Another major part of Boltzmann's work was his description of the second law of thermodynamics. So thinking of it as a tendency for systems to increase in entropy, to increase in disorder through time. So this is a consequence of probability again. If you're bringing statistics in and you're looking at these huge numbers of particles, and you're saying, well, what is the probability of the particles in a system, such as a gas, being in an ordered state versus a disordered state? So an ordered state would be something like they're all clustering in one particular part of they're clustering around in one part of the gas, versus to just being dotted around at random all over the place. I mean, you could say, well, both of these are random, but this one is far more ordered than this one. We can think of it as well in terms of usable energy. This is something that we were discussing when in the video on entropy. So, have you got some kind of usable energy? Have you got a concentration of energy in one place that could then do work while it's spreading out? And that's what's happening. If you've got the energy concentrated in one place, then it will tend to spread out from this ordered state into a disordered state. And Boltzmann added a whole new twist to all of this second law of thermodynamics in terms of thinking of it in terms of entropy and disorder. So yeah, I mean, that was a big change as well, because as I was saying in that video on entropy and the laws of thermodynamics, it's adding an arrow to the time of physics here. It's adding a direction of this is the way that systems will tend to develop through time in the universe. They won't go from being disordered to ordered. They'll go from ordered to disordered. So this is a change from the Newtonian mechanics that we were looking at previously, where there isn't a preferred direction. It doesn't matter which direction all the objects are moving in through time. Forwards in time and backwards in time look much the same. Here we've got a definite difference in what makes something move forward in time. It's that the energy is spreading out. It's that the entropy is increasing. It's that the disorder is increasing. These are all the same thing, but they're all adding an arrow of time to the evolution of a system. So so massive breakthroughs there, which Boltzmann was pioneering. So of course he's also commemorated in the Boltzmann constant, the 1.38 times 10 to the minus 23 joules per Kelvin, and fittingly so, because that is the constant that is providing a link between the classical and the modern in thermodynamics, between the macroscopic and the microscopic, between the macroscopic temperature of an object and the microscopic energy of a particle inside the substance. So it's linking all of that together. So it's it's a very fitting constant to be named after him. I mean, I suppose the other thing to say is really all this statistical stuff. Won't be surprising to hear that this was laying the foundations for a lot of what was going on in quantum mechanics. Quantum mechanics was coming into view on the horizon here at Boltzmann's tragic death in 1906. So you think 20 years after that, we were really getting into the midst of that massive paradigm shift through relativity and quantum mechanics, and you had all the big names then coming up with these new statistical descriptions of what was going on in the universe at the microscopic level. So Boltzmann was really a groundbreaker in that sense as well, a pioneer leading these other scientists into a whole new field of physics. So quite the guy really. So another good name to add to the list of important people in physics.